All right, recording is rolling. It's Monday, November 13th. I got a Kahoot for you guys on momentum. These are conceptual questions. So a lot of you guys already have out chapter 9 puzzles that we started doing last week. Printed on the opposite side are the conceptual questions if you want to follow along, same ones we're going to be doing. Okay. Then I think tomorrow would be a good day to wrap up those chapter 9 questions. I do want to fit in the bouncy ball lab with you guys, coefficient of restitution. So probably Wednesday, I'm thinking. Right? Now, been telling you guys that this Friday we're going to have an in-class quiz on both energy and momentum. So I think probably Thursday I'll do a review with you guys on those two sections. So energy and momentum. So pretty much, yeah, we're doing last few weeks of stuff. Right? I was originally going to give you guys an additional take-home quiz for momentum. I think we could go ahead and just skip that because, well, I mean, a lot of the same type of information is going to be embedded in this in-class quiz anyway, right? But yeah, I know we got a Thanksgiving break. Thanksgiving break coming up at the end of this week. So okay, well, we'll just do the in-class quiz and call it a day on momentum then. Right? And so that's how we're going to do that. Right, switch over to Kahoot. Oh, let's you guys all ready to go. Ready to go. All right. All right. So the momentum of an object defined as yeah, mass times velocity. Mass times velocity. All right, so a couple of guys picked the blue one. Guys, what is velocity versus time? What does that tell you? Velocity times time interval. All right. How about this? You're in your car, you're driving on I-95, 70 miles an hour, 70 miles an hour, and you do that for 3 hours. Hey, 70 miles an hour, that's a velocity. 3 hours, that's a time. 70 times is 210 miles. Is that like a displacement? Displacement, right? Okay, so there you go. Right. Mass times velocity. Okay, so you guys remember? Let's see. Last week we were talking about momentum. Momentum is mass times velocity. You could say a force times time interval would be an impulse. That'd be like a transfer of momentum, right? And let's say, I don't know, maybe a couple years from now, some of you guys are doing a science major. You have to take physics in college. What type scenario do you care about where you would actually care about quantifying mass times velocity and start keeping track of momentum? Whenever you see a what happening, a collision, something to do with collisions, right? Or sometimes explosions, right? So collisions, we're on to collision physics. Sometimes the chapter of a physics textbook is just called momentum and collisions. I got Kelly and Caitlin. Points on the board. Momentum of an object changes. What's going on? There you go. Right. So mass times velocity, that's changing, but the mass staying the same, which is usually the case. Yeah. Then the velocity must be changing. The velocity is changing. Right. But you know what? If velocity is changing, that means it must be accelerating, right? Because acceleration is rate change of velocity. And if it's accelerating, there must be a force. So yeah, the red, blue, and yellow answers, those all go hand in hand, right? If one's true, kind of all three are true, right? Yeah, you guys got that. All right. Points. Table tennis ball launcher is fired. You know, compared to the force on the ball, the force on the launcher is same for one winner. I wonder who got that. Same force. Same force on the launcher as on the ball. Ooh, that goes back a few months in this class. Oh, guys, that's called Newton's what? Third law? Newton's third law. For every force, there's an equal and opposite reactive force. Right? Two objects pushing against each other. Here's the ball and the launcher. Right? Who got them points? Oh, Paige. Moving to the top. Right? I think it's a setup for this next question, though. Let me help you guys out a little bit. Right? I think I remember the next question. Right? So if the force is the same, right? Well, one's to the right, one's to the left, so opposite directions, but the magnitude of the force is the same, right? does the time interval of that force, is that also the same? Here, I'm gonna switch my screen over. And you guys, something here. Maybe I should have started with look at these questions without momentum, mass times velocity. That's the first question. Collisions, it's conserved. But I'm really here's the one I'm looking for. Here's what I'm looking for. Right. So the force on the launcher versus the force on the ball. Maybe the force on the ball is like this, and the force on the launcher would be the same graph but upside down, because opposite direction, right? Right. But that force would have to be act for the same time interval, right? Right. Right. Which means that both the ball and the launcher get the same magnitude of this delta p, which is called impulse, right? The change of momentum. That's it. Here. Change momentum. It's called impulse. Right? It's opposite directions, but the same magnitude. Let's see if that is the next question coming up. In which case, I hope everybody gets it right. Tabletop tennis ball launcher is fired compared to the impulse on the ball, the impulse on the launcher. So if you guys get this. Is the same. Yes, same impulse, right? The same force for the same time interval, force times time interval. There's your impulse. Right? Now, impulse is also equal to mass times velocity, or mass times change of velocity, right? So they both get the same version of that too, right? You know what? Here, let's switch over. Let's switch back over here. Okay. So you guys are gonna get that. Okay. All right, let's draw this out. Draw this out because it's not quite clicking yet. Okay. So here's your launcher. Ooh, so a little cannon, right? Right, and then you got the ball. Right. Well, now the force really only applies while it's inside this cannon, but right. So while it's a cannon inside the barrel, right? So pow, right? So right. So let's say you have a little tiny mass times a huge change of velocity. So now it has a huge velocity because it started at rest, right? Versus this launcher has a huge mass, but it gets kicked back with the same force, right? But now only a small change of velocity, so it's not moving back very fast, right? You guys see these both have the same magnitude of momentum, mass times velocity, just one's to the right, one's to the left, so one's positive, one's negative, right? All started at rest. There was zero momentum to start out with. I guess that, right? So it's the same force for the same time interval, which resulted in the same mass times change of velocity, but different masses, different final velocities. Who got points now? I got Finn, Caitlin, Natalie, Paige, and Kelly. Collision is considered elastic if what? Yeah, those are all properties of elastic, especially that gold one. Like if I had to pick one as like the best answer of those three, yeah, definitely that gold one. Right, kinetic energy is conserved. That's what we've been using to mark that out. Right, elastic. Example is Newton's cradle right here. That's pretty close. Probably about as close as I'm going to get to elastic. Right, like perfectly bouncy. Right, not only is momentum conserved, but kinetic energy also conserved. Right, all those other things too. All right. Got Jackie, Paige, Caitlin, Natalie, Kelly. Suppose standing on a pond, there's no friction between the ice and feet. How do you get off the ice? Yeah, you have to throw something in the opposite direction. Right? Remember the Magic School Bus clip from last week? Magic School Bus clip. They were on a frictionless field, which is basically that scenario right there, right? Whenever you're talking about like an ice rink in a physics book, they're basically getting rid of the friction, right? And like everyone who was a fielder, right? They were just kind of stuck in place. Right? They were trying to run somewhere, but there was nothing to push against, so they were just like stuck wherever they were. Right? The only way you could, you'd have to like take your hat or your glove off and like throw it in one direction, so you could go back the opposite direction, right? Right. And then if you did that, the center of mass. Let's say you took your baseball mitt off and you throw your mitt off like right? The center of mass between you and the mitt still stays in place, like wherever, right? The mitt just goes one direction and you very slowly go the opposite direction. So how that would work. All right, Kelly on fire. Freight train rolls along a track with considerable momentum. If it roll to roll same speed but twice the mass, what would its momentum be? Twice as much. All right. Here, we're gonna draw this one out too. Let's bring this over here. Okay. Let's look at some freight trains. Freight trains. Here's some more freight train questions coming up. So got this freight train, little wheels here, right? Okay. So like some mass and like some velocity, mass times velocity, right? Well, its momentum then would be mass times velocity. Okay. You guys see if you double the mass, you're going to double the overall momentum. Momentum is P, right? Momentum. Okay. So suppose you have like 1,000 kilograms at 1 meter per second. Well, if you have so 2,000 kilograms at 1 meter per second, okay, double that, doubles the whole thing. Okay. What if you here, make it my own questions here? What if you double the velocity, but you leave the mass the same? So mass the same, we're going to double the velocity. Does that also double the momentum? Yeah. Right. Let's look at a different property though. You guys remember every once in a while we've been reflecting back on kinetic energy. That's like this right here, 1/2 mv squared. Right? Because it's the same ingredients, right? Mass and velocity, same ingredients to make these things, but we just rearrange them different ways, right? Like baking cookies versus brownies, right? Okay. So suppose you double the velocity of this thing. What happens to the kinetic energy? It doesn't double. It increases by what? What is double squared? It's like 4 times the energy, right? And then the classic question that I've probably asked you guys 5 or 10 times before, but let's see if you guys remember those, right? Is what happens to the braking distance by doubling the speed? If you double the speed of this train, what happens to its necessary braking distance? Goes up by a factor of 4, wouldn't it? Right? Which is that's last section questions, right? But you guys are gonna have a quizzes at the end of this week that involves both energy and momentum, so maybe that's a good review question for that too, right? All right. Did some extension questions with that one. All right, we got Finn, Caitlin, Paige, Natalie, and Kelly. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because why? So the force against the cannon is relatively small. The impulse on the cannon is less than the impulse on the cannonball. The momentum of the cannon is unchanged, or the cannon has far more mass than the cannonball. That's the answer there. Yeah, look at you guys go. Right. That sure looks a lot like that table tennis ball launcher. Let me switch over and give you guys the visual on that again, right? Okay. You guys remember the table tennis ball launcher versus the launcher versus the ball, right? Well, it could just be a cannon and a cannonball, right? It's the same thing, right? So they both experience the same force for the same time, the same impulse, just opposite direction, same magnitude of impulse, right? But a large mass has a lot of inertia, small change in velocity. It just slowly recoils backward while the cannonball really fast to the right. Different masses, right? Same force, different masses, right? Different accelerations, different final velocities. Right. All right, Natalie, on fire to the top. Order to catch a ball, a baseball player moves his hand backward in the direction of ball's motion. Ooh, doing so reduces the force of impact on the player's hand, principally because why? Oh yeah. All right, you guys got that. All right. The time of impact is increased. I think we did talk about this last week. So let's be on this too. Things over here. Okay. So we got like glove. Here's the ball coming in real fast. Right, it's gonna bam, it's gonna go to a stop. Right. So the ball has some mass and some velocity starting out, right? It's going to be mass times change of velocity, right? So the impulse is mass times change of velocity. That comes from a force applied for some time interval, which was that poster I just showed you guys a minute ago. Let me find it again. Here it is. Right, and think back to this poster again, right? There's some kind of change in momentum. Think about this, right? Force times time interval. Right. So let's throw some numbers in here. Right? The mass of the ball is whatever it is. And its change velocity, you also cannot change, right? I gave you guys a similar story last week of if you have to jump out the third window of a burning building, would you rather land on the concrete or on trampoline, right? And none of this stuff changes, right? None of this stuff changes. None of this changes, right? But what you can do, let's say this comes out, I'm just gonna make some up, right? Let's say this is like 1,000 units, 1,000 kilogram meter per second. Right, something like that. I'm just make some crazy up, crazy for baseball, whatever. Right? You can have, say, a large force, let's say 500 newtons, for a small time interval, like 2 seconds. Right? Or you could have a smaller force, say like 100 newtons, for an extended time period, like 10 seconds. So like the concrete versus the trampoline extends the time period, right? Or like an airbag in a car, it extends the time period of the collision, therefore decreasing the force, right? Or if you move your hand backward while you're catching the baseball, you extend the time period, therefore decreasing the force of the catch, right? It's the physics interpretation of that. All right, you guys did pretty good on that. Ooh. Right. Natalie is still on fire in the lead. Car traveling along the highway needs a certain amount of force to bring it to a stop. More stopping force could be required when the car has what? Yeah, there you go. Right, so all those would be true. Yeah, more force. Right? No, you probably remember too that the a lot of these variables actually end up canceling out in terms of the stopping distance, right? If you have a light car versus a heavy car, and all else equal, so if they have like the same tires and the same road and the same initial speed, blah, 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 right? But the only difference is a light car versus a heavy car. Remember, those have the same stopping distance, right? But the heavier car does need more force to come to a stop. It's just that in all the ratios, it ends up being the same distance at the end of the day, right? Yeah. Heavier car has more inertia, more momentum. So, all right. The force of an apple hitting the ground. Ooh. Yeah, all the above. Okay. The faster it's moving when it's about to hit the ground, that's gonna correspond to more force. Okay. Also, the time of impact with the ground. Now, we just kind of talked about that with the like catching the baseball or like jumping on a trampoline versus the concrete ground, right? If you can extend the time of impact, that decreases the force. Right? But hey, whether or not the apple bounces. Now, this is also something we talked about last week. Here, gonna draw this out. Let's draw an apple falling down to the ground, right? So we got big old apple tree, got this apple here. It's gonna, right? And maybe it like falls on a scale. Ooh, a scale can measure some kind of force, right? That's what a scale is good for. Right? So the apple gonna fall down. Here it is, like mid-flight, it's like falling. Right? It's gonna do something here, right? So what force are we talking about? Well, okay, I see there's gonna be a collision going on. So say in the future you're taking physics in college, think, okay, I see there's going to be a collision. So I'm already thinking in terms of momentum impulse. I know that's mass times change in velocity, right? And I know that's also equal to average force. It's called average force for the time interval of that collision. Right? Delta t, change of time could be time interval, right? So the more massive the apple is, the more force there's going to be, right? I see a direct relationship there, right? If it's triple the mass, it's going to be triple the force, right? So I'm gonna do with this, right? No, the change in velocity, right? Because there's some velocity it picks up to where it was hit the scale. And well, if it comes to a dead stop, suppose you have like a suppose the scale is like mud and it comes to a dead stop, like inelastic collision, right? Then the change of velocity would just be that speed minus zero, zero minus that speed. Okay. Right. The greater change of velocity, the greater the force, right? There was also, okay, and then they said something about time interval, right? So this was like my example before here, right? These two variables, anytime two variables are multiplied together on one side of an equation, that means they have an inverse relationship with each other. See how like if one goes up, the other goes down, right? Like as the time interval goes up, the force goes down to equate to the same product, right? Now there was one last option that would, and this was all the above came out to be the answer. There's one last thing, whether or not the apple bounces, right? So what if the apple sticks versus if the apple, I'm gonna draw a side-by-side scale. So we're like do a side-by-side scenario. The apple, boing, like bounces, right? What's the difference in force, right? Let's say it was come down at here. Just tag some numbers to this because I bet some of you guys see this, but in this case not everybody. Right? What if the apple was falling at like 5 meters per second, and then goes to 0 meters per second? First, that's if it sticks. Right? Do you guys see a change in velocity? Well, I'll just call it 5 meters per second. It's be negative, but whatever. Right? But what if the apple was coming down at like 5 meters per second, and it boing rebounds at like 3 meters per second? And don't forget that these are these are vector quantities, so direction matters. I just labeled the magnitudes. Guys, what is the difference between 5 down and 3 up? And don't say 2. What's the difference between 5 down and 3 up? What is 3 minus negative 5? 3 minus negative 5. Is that like 8? 8 meters per second? Ah, so if you compare this to, we talked about this last week, so it's probably in your notes already, right? If something boing bounces, that's a greater change of velocity, isn't it? Right. Now let's go back to this guiding equation to figure out what that means for the force, right? So, okay, the mass of the apples, whatever it is. Oh, that's a greater change in velocity. And that has a direct relationship with the force, right? In fact, if this was perfectly elastic, it might bounce all the way up to 5 meters per second, in which case the change would be 10, right? 5 minus negative 5 is 10. You could get up to double the force by bouncing compared to sticking. Okay. Right? You guys remember that? All right. So the extension idea there, but you guys got that. That's all the above. All right. Yeah. Oh, that's what I was going to ask you guys too, right? Would there be more force associated with sticking or bouncing, right? Let's see if you guys remember what I just told you, right? Let's see, show hands, right? Is there more force from sticking or more force from bouncing? Right, show hands. How many say more force from sticking? How many say more force from bouncing? Bouncing. Ah, God, there's my winners. More force from bouncing. Bouncing is more force. All right. Moving freight car runs into identical car rest on a track, so same mass. The cars coupled together. Compared to the velocity of the first car before the collision, the velocity of the combined cars after the collision. Ooh. Ooh, half as much. Just a couple of winners there. All right, let's switch over and see why. I do have a cart already drawn here, so let's just continue with this one. Right? Let's say there's another cart just sitting on the track. It's and it's the same mass, right? So that car's mass m, that car's mass m is coming at some velocity v. Right? Let's ignore the kinetic energy right now. Right? I'll give you guys some numbers. How about that? Let's call this 1,000 kilograms. This would also be 1,000 kilograms. Okay. Let's have this going at about 30 meters per second. And this has an initial velocity of like 0 meters per second. Okay. So these cars are gonna bam collide, and it says couple together. So that's perfectly inelastic, right? Like they stick together. Okay. Let's find the poster I gave you guys on that one. That looks a lot like this. Okay. Actually, it's a little bit simpler than this because one car just starts at rest. That's like doing this out, right? Oh, your guys' previous lab, your last lab, the last lab you guys did. You had collision cars. How do you guys doing? Basically, this right here. Okay. So this is like your lab. So we're doing. I'll start with the framework. Sum of momentum before the collision is equal to the sum of momentum after the collision. So whenever you see a collision in physics, think, okay, well, momentum is conserved. I can use that as a starting point. Your lab, I had you test this out, but we're going to start this as a starting point. Okay? Right. So that's mass times velocity. And it looks like it's all coming from this cart. So let's together, right? Is equal to, and I got the two carts stuck together. Would that be 2m, right? M plus m, because they said identical carts. The word identical in physics is going to be like same mass, maybe same other properties too. Right? Okay. And then times final velocity. Right? And the question is, what is this final velocity compared to the initial velocity? Okay. Oh, you might be able to see it before I even plug the numbers in. Because guys, what's m divided by 2m? The m cancels and you get 1/2, right? 1 divided by 2 is 1/2. If you need some numbers, let's plug some numbers in. It causes 1,000 kilograms, moving at 30 meters per second. Goes to 1,000 plus 1,000, that's like 2,000 kilograms. We double the mass of what's in motion. Right? Double the mass of what's in motion, but it has to have half the speed. Right? Divide the 2,000 over, that's 1/2, 30 meters per second. It's 15 meters per second is final velocity. You guys see that? Right? Got half the original speed by doubling the mass. Double the mass, half the speed, right? Because momentum is conserved. Momentum's conserved. All right. All right, I got Paige, Finn, Kelly, Caitlin, and Natalie. Piece of putty moving with 2 units of momentum strikes and sticks to a heavy bowling ball initially at rest. After the putty sticks to the ball, both are set in motion with a combined momentum of 2 units because momentum is conserved. Right, so inelastic collision, but regardless, regardless of what kind of collision, momentum is conserved. But this is inelastic, so they're all moving together with the same momentum that we started with, right? Maybe that's 2 kilogram meter per second or something like that, right? You guys good there? Here, I want to draw you a picture before I hit next because I'm pretty sure I know what the next question is too. Okay. I think this is going to be kind of like remember the apple sticky versus the bowling bouncing, right? I think you guys are about to get a very similar Kahoot question. To do a couple of bowling balls. Say this bowling ball's on the floor, this bowling ball's on the floor. It looks like a bowling ball, right? Okay. What if I have a piece of putty moving in, sticks to it, and the whole thing starts rolling, right? Versus, what if I brought a bouncy ball that boing bounces off and then gets this one rolling, right? Which one of those is the bowling ball rolling faster? I forget exactly how this next question was phrased, but I think some version of that. All right, let's see. See how what we're doing here. Yeah, bouncy ball with 2 units momentum. A boing bounces off the heavy bowling ball. After the bounce, the bowling ball itself is set into motion with the momentum of what? Yeah, more than 2 units. More than 2 units. Right. So tag some numbers to like just do here, right? Let's say this was coming in this way with like 2 kilogram meter per second. Okay. Well, that means that after the collision, the whole thing moves off with also 2 kilogram meter per second. Now, if you divide by a huge mass, that's a small velocity, but okay, whatever. It's a motion, right? Let's compare that to this guy right here. Suppose this is coming across with 2 kilogram meter per second. and then the boing rebounds with, oh, let's say like -1 kilogram meter per second, something like that. Guys, what is the difference between 2 and -1? What is 2 minus -1? 3. Ah, I see 3. Okay. So then this actually rolls off with, try not to give the answer away by drawing this too accurately before, like 3 kilogram meter per second worth of momentum, right? Because this had a, well, right, the momentum would be conserved, right? So whether you say like the impulse, like the change in this one is equal to the change in this one, which is 3, right? Or if you do before versus after, what's the momentum, right? So before it was 2 units. After it's 3 minus 1 is still 2 units, right? So either perspective, right? Now there's one more thing you'd have to check, because you're gonna say, well, this looks like extra momentum. Where all that come from, right? Is you would check kinetic energy. So you say, if I add up all the 1/2 mv squared before and after, right? And then remember, you can't add energy to the system. So there could only be up to the same number of joules worth of mechanical energy in the system post compared to pre-collision, right? Probably go down a little bit realistically. If this was perfectly elastic, then equal number of joules in the system, right? But you can't create energy. So that's like the additional consideration you have to have. But yeah, the bouncy situation, yeah, would roll off faster than the sticking situation. All right, I got Paige, Finn, Caitlin, Kelly, Natalie. The force that accelerates a rocket into outer space exerted on the rocket by. Yeah, exhaust gases, right? The rocket pushes on the gases push on the rocket. Maybe that's more of like a Newton's third law kind of question, right? Equal and opposite forces. All right. Cannonball shot from a long barrel cannon travels faster than one from a short barrel cannon because cannonball receives a greater what? Yeah, impulse, impulse. I do want to draw this one out. Most everybody got that right. So we're seeing a couple of side-by-side cannons here, right? Short barrel cannon versus like a long barrel cannon. All right, side by side. Okay. Yeah, this one send the cannonball faster and further than this one. Okay. So it could be the same force, like the same magnitude force, right? So there's like some chemical explosion. There's whatever they're using to explode this thing, right? But on the short barrel cannon, as soon as the cannonball leaves the barrel, well, that force is no longer acting on it. Right now, it's just a projectile. Now it's projectile, right? But this one here, right, that force continues to act on the cannonball for a lot longer time, right? And then at this point, finally turns into a projectile, right? Yeah. So remember, impulse, transfer of momentum, mass exchange velocity, that comes from applying a force for some time interval. It could be the same force, but if it's like 3 times the time, it'll also be 3 times the change of momentum. There you go. 2-kilogram ball thrown at 3 meters per second. What's the momentum? Yeah, 6 kilogram meter per second. Right, you just multiply it, right? Mass times velocity, right? 2 times 3, and then the units also follow. There you go. 6 kilogram meter per second. 4-kilogram ball has a momentum of 20 kilogram meter per second. What's the ball speed? Yeah, 5 meters per second. Right, so 20 divided by 4. Then all the units also follow, right? Okay. 4 times 5 is 20, if you like that. All right, I got Paige, Natalie, Caitlin, Finn, and Kelly. Ball moving at 6 meters per second has a momentum of 24 kilogram meter per second. What's the ball's mass? Yeah, 4 kilograms. Right, 4 kilograms, 6 meters per second gives you 24 units of momentum. All right, and for the win. While roller skating, Granny collides with her tiny grandson, Ambrose, who is at rest. Ignoring any friction, Ambrose's speed after the collision will be greatest when what? Yeah, the boing, and they bounce. Right. This is the same thing as the apple bouncing off the scale versus sticking to it. This is the same thing as what example do we use? Oh yeah, the putty against the bowling ball versus the bouncy ball off the bowling ball. Yeah, if you bounce, that's more forces involved, and a greater final velocity. Yeah. All right. Oh, wait, was that not the last? Wait. Oh, okay. This last question. Last question. If all people, animals, trains, and trucks all over the world began to walk or run towards the east. By the way, the Earth is already spinning west to east. That'll help you out a little bit. The Earth is already spinning west to east. So what if everybody started walking towards the east? Don't pick the yellow one. Don't pick the yellow. Look for either the red or the blue. One winner. One winner. Ooh, Earth would spin a little bit slower. A little bit slower. All right. Now, can people actually affect the rotation of the Earth? I do know an example where that actually has been the case. Do you guys know the Three Gorges Dam over in China? Right, so it's like one of the biggest dams ever built. Right, well, it's collected so much water that there's so much mass water that's been moved so far from Earth's surface. It's actually uh, slowed down the rotation of the Earth a little bit. Right, so yeah, people can affect the rotation of the Earth a little bit. Right, let's switch over and um, draw this one up. Right, so got one of you guys figured this out. One of you guys figures out. Right, so here is the Earth. Right, equator, North Pole, South Pole. Okay, so we got all this going on. Okay. Now the Earth is already spinning west to east, which is like this direction. The Earth is already, whether I call that V or omega, right, or something like that, or spinning that way, right? That's why here, like if you're standing right here, you still have to think this out. Right? You guys know the sun rises in the east, sets in the west, so the sun's like sitting here, right? And then as the Earth is spinning that way, that would make it appear to rise in the east and set in the west. Okay, so right. Now, what if you have like a bunch of like trains and people and blah, 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 like everybody starts walking towards the east, right? There's a few ways to analyze this. One way you could analyze this in terms of forces. Like if you're walking towards the east, you're pushing the ground beneath you towards the west, which is opposite of what the way Earth's already spinning, which would slow it down. Or you could do conservation of momentum. Now, this is more of a conservation of angular momentum type thought, right? So you guys remember how momentum is mass times velocity, right? When you guys come back from Thanksgiving break, we're going to do rotational dynamics. There's also momentum in an angular sense. We're going to call that capital L. This is called angular momentum. So this question is kind of a good preview for December days. And that's, you can make a really similar looking expression. So instead of mass, it's rotational inertia, right? Remember those rotational inertia sticks that passed around a while back? Right? They got masses taped on different places. Right? If you pick them up blindfolded, it's like, well, they feel like the same mass the same weight. If you shake them back and forth, right? It's like, they got different inertia and a rotational sense. Right? That's like this I-dye, the whole like sphere of the Earth, the roller, right? So, times omega, right? Which is, you guys remember from a few weeks back, that's how fast the Earth is spinning, right? How fast rotating, call that omega, right? So like that. Okay. Okay. So this is also conserved within a system. Now, this one's fun too. You guys ever seen like Winter Olympics ice skaters, right? If there's some like ice skater, right, and they're like going to a slow spin, and then they bring their arms in, right? And what happens when they bring their arms in? Right, they spin faster, right? Right. So this is kind of related to this. I'm just planting some ideas for a few weeks from now, right? Something like this, right? Right. But not exactly this, because this is more like the Three Gorges Dam example I was telling you guys about, right? Three Gorges Dam. Over in China, they built this dam. It collected so much water, it raised the water level so high that it kind of went from going from this picture on the right to this picture on the left, kind of slowed down the Earth a little bit, right? So this isn't exactly that, but it's kind of similar idea, right? Right. So yeah, if everything on the surface is like moving even faster towards the east, then the ground beneath it can't move as fast, so that this whole angular momentum is collectively conserved for that entire closed system, right? Of like the ground beneath plus everything on the surface, right? So yeah, that's a little tricky one there, but that one's pretty fun to think about. If everyone started walking towards the east, it would slow down the Earth a little bit. Okay? Now that's only while everybody's in motion. As soon as everybody stops, then the Earth just resumes its regular spin rate. Okay? But that's not true for Three Gorges Dam, right? Because that water level's like permanently raised, so the Earth is going permanently a tiny bit slower, right? Because of its rotation because of that. Let's see, who won this thing? To the podium, the bronze, Caitlin, with the silver, and the gold, Kelly. I got Natalie and Paige. Where's up? Nice job, guys. Nice job. Okay, since we got a couple of minutes here, I think this book has, find a momentum question here. Looking for, I know which one I'm looking for too. Here it is. Jocko has mass of 60 kilograms, stands at rest on ice. Ooh, on ice. In a physics textbook, on ice really means like that magic school bus baseball field where there's no friction, right? No friction. Okay. Catches a 20-kilogram ball that was thrown at 10 kilometers an hour. It's about, what is that, about 6 miles an hour, I think. So 10 kilometers an hour. How fast did Jocko and the ball move back across the ice? Okay. Spell this one out here. Does that look like an inelastic collision? I think it's probably something kind of like this, but even simpler. Just Jocko starts at rest, right? Okay. Let's do, let's do some mental math before I actually write numbers down. Okay. That ball is a quarter of the total mass in the system, isn't it? Right? 20 compared to, well, 80 total kilograms, right? 60 plus, right? So that ball has a quarter of the total mass. So I'm going to guess that they slide together with like a quarter of the speed of that object, right? Let's see if the numbers play out that way. Sum of momentum before the collision equals sum of momentum after the collision. And go the mass of the ball times the initial velocity of the ball equals mass of the ball plus mass of Jocko times velocity final that we're solving for, right? Okay. So put some numbers in here. I got 20-kilogram ball going at 10 kilometer per hour equals a 20-kilogram ball plus Jocko's 60 kilogram. Be final. Okay. Yeah, 2060 is 80. Divide 80 over 20 over 80. That's like a quarter. It's like a quarter of the original 10 kilometers per hour is velocity together. So that should be like 2.5 meters per second. You guys think 2.5 meters per second? Okay. Let's check, make sure that's the answer. That's the answer. Yeah, 2.5 kilometers per hour. Whoops, I messed up my units right at the end. Kilometers per hour. I'm so used to doing meters per second. Right? Kilometers per hour. There you go. All right. All right. And that is a wrap on today. All right, you guys have a good Monday.